Já tá. Okay, I believe that we can start. Good afternoon, ladies and gentlemen. On behalf of the SP Portugal, I would like to welcome you all to our second webinar in the oil and gas series, the third webinar in the year. My name is Claudio Tejerina. I will be your host, and today we will talk about digital rock analysis for reservoir characterization and decision making. We have two guests of honors today, Caroline Mignon and Santiago Dressler. I will start introducing Caroline. Caroline holds a bachelor's degree in geology from the Federal University of Rio de Janeiro in Brazil, a post-graduation in marine geology from Utrecht University in the Netherlands, and an MBA from Getúlio Vargas Foundation in Brazil. She started her career in the oil and gas industry in 2013 as a researcher for pre-salt characterization at Petrobras Center. And then she started leading Halliburton's Brazil Digital Rock Office from 2018 and 2019, acting in commercial and development projects by applying technology for reservoir characterization. And Caroline currently is Halliburton's Digital Rock Solution Advisor and Business Developer. And then we have Santiago Drexler, who holds a Bachelor in Chemical Engineering from the University of Buenos Aires in Argentina, a Master from the University of Oklahoma in the United States, and a PhD from the Federal University of Rio de Janeiro, where he was also a guest professor in petroleum engineering for almost 7 years, and actually Santiago was my professor. He started his career in the oil industry in 2012 in chemical enhanced oil recovery with Petrobras. Then he moved on to reservoir engineering and petrophysics through the design and implementation of a SCAL lab in the Federal University of Rio de Janeiro. He is currently a principal engineer and development team leader in Halliburton, where he's integrating digital core analysis and SCAL to reservoir evaluation purposes in a variety of challenging places across the world. So once again, Santiago and Caroline, thank you so much for being here. And with no further ado, the floor is yours.
Thank you, Claudio. Thank you for the introductions and for the invitation. Okay, so can you just confirm me that you all are seeing my screen and hearing me well?
Yes.
Great, thank you. Okay, so let's start. Before we start, as usual, I'm going to share a very quick safety moment. And just regarding, it's really hard to talk about safety moment without talking the COVID-19. So just it's more a kind reminder than a safety moment, but just regarding that, we're seeing a lot of efforts in the globe to bring different types of vaccinations, of vaccine types being distributed, and it's a global effort. And it's just a kind reminder that there are many different types of vaccines and many types of organisms and different types of bodies and people, right? So just a reminder that the different types of vaccines and different types of people can have different reactions, right? So just a kind reminder for us to understand that our colleagues or our family members cannot have the same reactions as ourselves once we take the vaccinations. And some of the reactions might be confusion and dizziness. So sometimes when you're working in the home office, we actually don't know what's happening with our colleagues and coworkers or families. So they're apart from us. So just a reminder that some effects can be quite harsh in different people. And just for us to remember this and keep in mind to ask someone if they're feeling well. And it can be a reaction of one of the shots that they're taking. Okay, so with that, I'll go through the content of the presentation today. The presentation will be divided into two sections. The first one will be presented by myself, and it's focused more on how digital technology can help on geological model, right? And afterwards, Santiago will present how technology can support decision-making and also in the production side of the reservoir characterization part. So to start the geological characterization model part of the presentation, I will start with some introductions. So with some basic concepts about digital rock analysis, the acquisitions that we do, how do we do, types of machines that we use, and what we can acquire, what we aim to acquire from those images. And then I'm going to present some examples of these applications inside a geological context. And afterwards, how do we use technology to do visualization, integration, and use multi-scale to get insights from our reservoir rocks. And I'm going to finish showing an example of how we build a digital rock typing. So just for so it starts from the beginning, right? So what exactly is digital rock analysis? So the approach here for the digital rock analysis is the approach for rock characterization, but using different types of imaging technologies in multiscale to capture and create a digital version of a rock model, right? And behind that reservoir, by that digital model, we aim to compute static and dynamic properties, but also to make sure that this volume that we are computing is representative of the flow units and the reservoir that you're trying to capture. So in here you can see an image in different types of gray, right? Different scales of gray. So we have materials with different densities, and this is represented in the CT image with different layers of grayscale. So here you can see your open pores in black. You can see some. Can you see my mouse? Okay, here. So here you can see open pores in black. You can see some organic material in darker gray. You can see your grains in solid, grains in light gray, and the material that is really reflecting the X-ray, like in really white, is the high dense material, right? And afterwards, once we have our pores captures, we can just segment our rock in the pore system volume three-dimensionally. So we aim to capture not just the geological features and understand how it's distributed inside the rock. We also aim to capture properly the pore systems, right? And we do that in multiple scales, starting from core, afterwards plugs, rotary soil core, or even cuttings and chips if we need to. So here's just an example of how this technology images and applications are distributed across the well life cycle. So for example, the digital technology has three main technology fronts, right? So here in the red box, we can see this technology fronts. The first one is how we apply the digital technology to improve our reservoir characterization and how we target the most productive rock to evaluate the rock quality, right? The second front, what we call the simulation engines, that will be the part that Santiago will explain better. So how we use technology to fasten and leverage results about dynamic and static properties. And the last one that we can use in most of part of all the well life cycle is how we use the digital technology to integrate all the data that we have in multiscale in just one interface to get insights from it. And the basically differentiator of how technology presents improvement on these areas is once we have the capability to go zoom in the rock and to do a proper downscaling, we can do a proper upscaling, right? So we travel within the rock from the cores into the nanopore system if we have to, and then we link back until we know that the representative volume is actually acquiring something that we need to characterize. So the idea here is basically once we get the cores or the rocks outside of the ground, it's a really, really major effort. We spend a lot of time, we spend a lot of money, and if we take cores from the ground, it's already from an interest interval, right, in the well. So we should at least take as much information as we can from these rocks. And there's not exactly what happens in the standard industry steps, right? We see a lot of cores just being degraded and losing a lot of valuable information that we can acquire from them. So just by imaging, you can take your first digital record of your rock, and after imaging 3D, you can start traveling inside the rocks in different scales and to actually extract very valuable reservoir key data from it. So that's the idea of the technology and how it's distributing the well life cycle. So just starting to show a little bit of how we acquire the images, right? So there's two types of tomography that we do to acquire digital rock images. The first one is a tomography, and the second one is microtomography. So in this one, it's the same as we go to a doctor to scan some part of the body to see if everything is okay, right? So the basic concept here is you have a rotating X-ray tube, so it's an helical system, right? So we have an X-ray source that is on the one extremity of the tube, and the detector that is in the other extremity. So we put the cores lay down here, and actually the X-ray detector are rotating around the cores. while the quartz travels through the tube with a certain velocity. So what that means, once we do this rotation and the table moves continuously inside the tube, this movement actually is dictating how much would be your image resolution. So basically, if the core walks 1 centimeter and we have one slice that goes through, the X-ray goes through the rock and can measure the different types of individual book density that attenuates the X-ray differently, right? And usually, if you can increase, put the movement of the table very, very, very slow, you can increase the thickness of your image. So it can go into 0.3 millimeters resolution, for example, or 1 centimeter resolution. I'm going to present afterwards what is the standard of the industry and how we use that to reconstruct the image of the core in 3D. And the second one is the microtomography. So the microtomography we apply more for small amount of rock, for example, plugs, sidewall rock cores, or cuttings, or trims, for example. But here the X-ray source and the detector are still, and what moves is actually the rock, right? And we have a stage that we can approximate approximate the rock from the X sources to give more zoom, or put it a little bit more far away to increase the field of view. And this will also have impact in the parameters of our scanning, meaning that once the velocity that the rock moves will also have gap 1 slice per millimeter, per centimeter, or per nanometer. And this will reconstruct the image of the plug in 3D in different scales, depending on the lens that you're using to scan and depending on the parameters of the distance from the source, detector, and rock. And here's just for us to have in mind how we measure these resolutions in the images, right? So the CT images that we are creating in Acquire here, it's a volume, right? So in a 2D image, we have the pixel as a range of the resolution of the image. So the voxel here is the Z element, right? It gives us the volume, the depth of the volume. So if you have every CT element, we have a XD and XY, which be your pixel in 2D. And now adding the D element, we will have the voxel. So here we have one example of one pore and being measured. Like here are the borders, and the last resolved cell of it will be our voxel. Here, starting to enter on the applications of the technology on a reservoir rock, right? So once we scan the rock inside a tube for tomography, for example, in this case, we use a resolution of 3 microns for voxel, and we scan in dual energy. So what dual energy means? We scan the rock with a high energy once you go in the tube, and with a low energy once it goes out the tube. And having this max and mean parameter allows us to calibrate the rock to actually see the attenuations of the bulk density and photoelectric factor along with the image. So this means that every 0.3 millimeters, we have a slice of the core being imaged, and along with the CT image, we can acquire with the same resolution the bulk density, the photoelectric log. And as we have a high resolution for those images, and we create a volume that we can actually attenuate and difference the type of contrast in the image, this means that we can apply transparency, for example, to investigate the laminations of the features that are inside the core volume. So things that we don't see when we are seeing the core section in 2D or a regular core description, for example. In this case here, you can see all the same CT image in 2D here, representative in 3D with a transparency applied. Then you can see the high dense material constructed in orange. Here you can see a barrier of the high density image shown in here. And this can be applied to attenuate every kind of geological structure that you're looking to evaluate. For example, vugs or open fractures, to see if they are connected in what X, and to understand how these features are controlling the geological features of your reservoir interest interval. Sorry. And sometimes when you work only with a 2D image, we don't actually understand how the heterogeneity is distributed in 3D, right? And this is a very good example of how heterogeneity can get really nasty when we go in this only 10 meters core interval, right? So this is a course interval on only 10 meters far away from each other, and you can see a lot of heterogeneity going on. So the grayscale here from the course, this is 1 meter course. The grayscale here actually density legend, right? So your open fractions and your open pores are in black, your high dense material is in white, and in between you can see in different shades of gray. So for example, you can see and check if one of your vugs or fractures are actually connected. And if we see this type of heterogeneity going on, we can see that actually where the grays changes, the rock properties will change, right? So your porosity should be inside of your dark gray material, and where you have more solid material will be more light gray. And today in the industry standards, we just sample in every feet, right? So we get like 3 to 4 plugs per core, and we don't actually know what we are drilling into when we are making a plug, right? And sometimes it can capture a big vug, or we can capture fractures that won't be representative of your flow unit or from your reservoir. And then you send the samples to the lab, you spend a lot of time, spend a lot of money, and sometimes you just increase your uncertainties by using these values, right? And it can get also a very bad input for reservoir model evaluation and reservoir prediction. So how the technology can support in this? This is an example of a pre-salt core, and where we can, for example, try to get some depth selected to see the plugs, right? So what the technology can do for you is just to extract a virtual plug out of it. So to actually see how your plugs will be before drilling it, right? So this was a virtual plug extracted from here, a volume, it was not physically cut. And you can see that the layers that we are trying to characterize are represented here in yellow and in green. And you can understand that this plug, we have a different value of connectivity, for example, in the EZ axis from the XY, right? For example, in this one, there should be a more open pores plugs. When we actually do the virtual plug, we can see there is a huge high density blob inside of the plug. And this can actually give you not so accurate results for your flow properties in this plug. This blob can just get in the way of you have a good accurate results. And here you can see a third example of a good plug, an homogeneous plug, when you can actually rely on the results of this plug, right? So you can use this tool to decreasing the uncertainties that you have from your petrophysical properties. And actually, you don't have just to. This doesn't make your plugs not valuable. You just can send, for example, for geochemistry experiments inside instead of scale measurements, for example, right? And here's an example of two plugs that are really close to each other. So this shows a good plug, and this shows what the plug that we were actually choosing before drilling it. So this fracture was not possible to see in the surface of the core. So we extract a virtual plug, and we could see that this plug will probably break before we taken it, or it was not going to be valuable, right? Here's an example of how we use this technology to see all the fractures. So you can see the fractures in red, Philly fractures, right, with high dense material. You can see the open fractures in black. You can attenuate the colors, the grayscale to color scale, to actually just use the contrast to understand what is going on inside of your cores, how the anisotropy is distributed, and see where to plug, where not to plug. And here on the left, you can see your whole well, right? The whole length of your well. You can select 1 meter of the core. You can investigate geological structures. See, for example, if you want to take a virtual plug from here, take. If it's not good, you can just go back, find another location, see again, and do it until you have optimized sample locations, right? And you can integrate other types of data as well. And it facilitates all the data management reservoir in multi-scale, and can integrate also with previous existing data, meaning that if you have thing sections, for example, you can also put inside of the same, all in the same user interface. And this can support us to have more insights about what we are dealing and which kind of material that we do have in hands. Everything on your computer, right? So sometimes even more even now during the COVID age, we're not allowed to travel or to get more close to rocks. So everything here is just accessible and in the same user interface, right? And with this type of resolution and 3D knowledge and the way that we can travel through the core in multi-scale allows us to have pretty good accurate information from the geological features. So here, for example, is just output from investigation of the core interval for fractures, right? So we can see how the fractures are oriented. If the cores are oriented, we can orientate the fractures. So see the dip, see the strikes, and the classifications of the fractures inside your resolution. So if you have a fracture in size 0.3 millimeters, you can actually see and classify it in terms of if the fractures is filled or if the fracture is healed, is the fracture open, connected? If it's connected, in what axis? What is controlling the flow? Is the fracture supporting, or is the flexion blocking the flow? If it's filled, if you have the fractures connected to a flow unit that is interest from your reservoir, if they have connection with bugs, and even what is the frequency of the fractures, right? To understand it, and we can create logs output, for example, out of this. So here we can see their CT image, and here's correspondent of frequency, fracture frequency logs from this course. But basically, as I showed in the previous video, we can do the same for every other geological features that are interest. So this example was with the fractures, but we can do the same, for example, with anisotropy, with laminations, or with textural controls, right? Depending on your reservoir challenge, the technology can really investigate with high resolution and create an output log to improve the resolution of your reservoir model. Another thing that the technology allows us to do as well is to input other data such as thin sections, right? XRD, XRF, and we can go through the rock. So here's your well, and here's the depth that we are trying, that window that we want to identify. Here's your core in 3D, and here's the plugs that you have. Here's the sub sample that you can get from this plug. This is the pore system in 0.2 millimeters resolution. And here you can investigate where's the mineralogy distribution inside of the thin sections of this analysis, right? So it can give you a really rapidly idea of what you're dealing with and to extract more information of the data that you already have, because you have everything in the same interface. And the rock typing starts with once we can acquire the image to understand the mineralogical distribution and to understand what flow units we're trying to get, right? So we understand that the different rock types and different flow units, we have different pore system controlling it, right? So once we scan, for example, we start with the plug scale, and then we enter in the 1 microvoxel, for example, and we do the same for all the rock types and flow units that we have until we have all the pore systems solved, meaning that we can see that with definition the borders of your pores. And not only in 2D, we create a 3D volume of it to guarantee that that is the correct volume to perform the computations of static and dynamic properties. So here's an example of the dolomite rock type, and you have not much compaction, not much cementation. We have open pores, so the porosity was solved in 4 microns per voxel resolution, for example. Here we see a rock type that we have dolomite, but in this case we have calcite filling the pores, and we have smaller size of pore systems. So we have to go further and further until we go into 1 microvoxels to actually find your pore system connected and with the borders well resolved until you get pearls to solve. And then we go to the other rock type that is calcite dominant only, and we have a pretty tight fabrics of your pore system, and we go and zoom in, and we zoom in again for 2 microns. We zoom in again from 1 micron, and we still cannot see your pore system is resolved. And sometimes you can go into nano resolution if that is meaningful of a reservoir and it is dominant of your rock type. You can go into nano resolution to see, to actually investigate what is the connectivity in this rock type. So here's just the same idea that I just showed you in 2D, but in 3D. So we do the same in all resolutions of the multi-scale from plug until we have the pore system solved. We create the rock volume. We create the rock volume and populate with the segmented pores connected in blues, with the matrix in red. And once we have that well characterized and representative, we know that this volume is actually, we also integrate physical data, as Santiago will explain later. But we have guaranteed that that representative volume is okay to go to the computations. And here's just an example of the rock type with multi-scale approach. So for example, here we can see the whole length of your well and what we call CT phases, right? So you have your book density logs in here, you have your PE logs in here, and we can cluster that to actually understand what phases is dominant on your well. So for example, we have 4 rock types in this well interval, and you can see that the predominant one is the representative in pink, and we can see all the characteristics of each one, right? So in the resolution that the pore system is representative, is the more close ones, the calcite one, and you can see the thin sections, and we can see the shift here of the pore size distribution characterizing that rock type. And you can see how it's representative in the core. So we can link all the scales of the rock type, and afterwards that we have the 4 types well representative in all these scales, we can compute and create trends for relative permeability, capillary pressures, and all the simulations that we do with different scenarios, wettability modes, and changing contact angles, for example. So just by having one sample, we can create a lot of production scenarios and to understand how these trends are actually controlling your reservoir model. And this will be the topic for the part that the technology supports the production scenarios that Santiago will move forward from here.
Okay, thank you very much, Carol. Okay, so I will start talking about how we can use digital rock analysis to support production and characterization of flow. So basically, what we will talk about in this part of the presentation is how we capture the pore space, and we use these digital volumes in order to perform multi-phase flow simulations, and how these simulations can be used to predict the flow capacity of each of the phases. And that takes us to what we call the digital scale of spatial core analysis, which is a way the technology can support the traditional petrophysical characterization in the laboratory. And then we will finish and wrap up with a case study that summarizes all these type of applications. So moving to the next slide, please.
Hi, Santiago. Sorry, I think my PowerPoint just crashed.
Oh, okay. No worries. I will share my screen here. You can move. Just a second. So can you see my screen?
Yes.
Yes, we can do.
Right. So as Carol was explaining in the last part of her presentation, we start from analysis at the core scale, and that analysis at the core scale integrated with another type of characterization, like for example, wireline logs, and sometimes we use formation tests and other type of informations at the well scale, we can come with a characterization for the rock types. And with the rock types, we need to understand what are the features that govern the flow for each one of these rock types. And for that, of course, we cannot work at the meter scale, not even at the centimeter scales, at the plug scale. We need to go to millimeters and then go farther in resolution, reaching micrometers and sometimes even nanometers, depending on the distribution of the pore sizes, in order to visualize what the pore size distribution is. So that's what we call the robust downscaling. So it starts with identifying the different rock types and the dominant features of each one of them. And then, as Carol was explaining, selecting the right plugs to represent each one of them. And then when we have the right plugs, we need to know how to zoom in. So that's what we will discuss a little bit in the following slides. We need to know which is a good region to get a good sample, a good subsample inside the plugs. And with these regions, we need to characterize completely all the dominant features of the pore system. So if that sample is complex as the ones we see here, for example, in the pictures here, we know that maybe not only one digital volume will be able to characterize the flow across that sample completely. So we need to know where to choose the subsamples and then scan them and in higher resolutions and resolve the digital volumes and then perform simulations at the digital volumes. Once we have these parameters calculated at the pore scale, we need to know how representative they are for the whole sample, and then how to integrate them and come back in scales to get meaningful information, because we don't want to get pore scale relative permeabilities or pore scale capillary pressures that cannot be integrated with dynamic models. We know that for reservoir modeling, we need to get at very, very large scales in order to be able to perform simulations for the whole fields. So it's key to know how to perform this robust upscaling in order to take the information we get at the pore scale and we integrate it with other sources of information, getting a useful data that can be used to populate dynamic models. So basically, all our workflow comes from how we can downscale robustly in order to know where to acquire the information. And then once we acquire this detailed information, how we can transfer scales without missing the key points. So now let's start. In this part of the presentation, we will talk basically more about the zoom in and part, and then how we can visualize the pore system, and then how we can simulate in this pore system. So as Carol was saying, at the core scale, we work with the tomography, X-ray tomography for the CT. But when we want to get to the pore scale, we need to go to the micro CT, and we need to reach resolutions that are compatible to what the pore throat size distribution that we have for each rock. So first, it starts with selecting the right subsamples. We will discuss a little more later in the presentation. But then once we have the digital volumes, we will image in the micro CT. And then after that, we need to analyze the data. So basically, what we need to do is data processing in order to get these 3D volumes that Carol was showing in the first part of her presentation, and use procedures to understand what is each phase of that volume. So here, for example, we can see in the image in the middle that this image is segmented into three different components. Basically, we have the matrix, solid matrix, and then we have two types of porosity: the porosity that is isolated in red, and then the connected porosity in blue. As we know, as in reservoir engineering, porosity and permeability basically are characterizations that are fundamental to know how what is the storage capacity of a rock, but also what is the flow capacity of the rock. So it's very interesting to get, after we get these volumes, to be able to do computations in it. And that will allow us to see what happens at the micro scale, at the pore scale, and how fluids will distribute within the rock, which fluids will be where, which will be concentrated in the small pores or in the trapped pores, and how easily they will be displaced one by the other, depending on the distribution of pore sizes, but also inputting some complex parameters that can account for wettability changes and properties of the fluid, like interfacial tension, that will be really significant at the pore scale. So going through the multi-resolution, so Carol showed how we can go in resolution, but in the large scales and get into the plaques scales. And now if we take it farther and we can see how we can resolve the pore system completely. The idea here is to get a fast characterization of the structure of the porous structure of the sample, and be able to capture the dominant flow system. So the idea is to be able to select elementary representative volumes that will be small, but that will be small enough, but then we will carry all the fundamental properties of flow of the whole sample. So of course, the more heterogeneous or the lower quality of the sample in terms of rock homogeneity, it will be a bigger of a challenge to find an REV. And sometimes we cannot find a one subsample alone that will represent the whole pore structure of the system. But the idea here is that if we have different pore pair conditions within the same sample, we need to find different subsamples, but overall, when we integrate them, we need to be able to capture all the features that will dominate the flow for that sample. So here we have two examples. Here we can see these are the scans, the micro-CD scans at the plug scale, what we call the plug scale, that is 40 micrometers per voxel. And we can see that they have a very different pore structure. Even at this resolution, we cannot actually define all the pores, but we can see that the sample on the bottom is much tighter than the sample on the top. So of course, when we want to resolve these two samples, we will use different resolutions to capture the pores. In this case, we see that going through this square that will generate the volume, and then we can scan this at a higher resolution of 4 microns per voxel. We will achieve a subsample in which we can see the pore structure, and we can compute actually the pore system and see how the connectivity comes along within this volume. For the sample on the bottom, the pore size distribution is much smaller, so we need to zoom in much more. So 500 nanometers per voxel resolution was needed to perform to be able to capture a connected pore system across the sample. But once we capture this and we get the pore system, we need to make sure that this is actually representative of the pore system of the sample, and that we achieve with quality control. And our quality control is very rigorous in terms of knowing, having standard workflows to statistically analyze how the distribution of flow properties is across the volume that we selected and across other parts of the sample, in order to consider if we are getting actually a volume that represents in terms of flow the whole plug to which it belongs. So now, once we get a volume that we trust that it's good enough to perform simulations at the pore scale, the first thing is to simulate what we call R-color routine cone analysis. That is what we use to support the static models. And actually, it's the solvers that use single phase flow. So it's a much simpler approach than when we use multi-phase flow. And here we will simulate and calculate porosities and permeabilities, and then also we can calculate electrical and elastic properties, like, for example, formation factors, cementation exponents, or VPVS. Here we have another example that is very different than the one I showed before, that were sandstones. In this case, we have a carbonate that we can see is completely heterogeneous. So this is what we call a multimodal pore system distribution, in which obviously there is not only one type of porosity permeability trend here, and we would need more than one volume to be able to represent this sample. So in this case, we can see that for the open pores here, we can go to a lower resolution scan, and for these tighter phases, we would need higher resolution scans, and we will get our own porosity and permeability, and then we could actually perform porosity permeability trends that will allow us to populate this across the system. In this case, for example, after we get this for one plug, we can extend this type of procedures and move further in order to get porosity permeability trends for the whole system that we are characterizing. In this case, in this column, we have a column that can have different depths, but it will be much larger than a plug scale in the meter scale. And by performing adequate poro-perm trends upscaling, we can get the different trends that will represent the different type of pore systems of the whole volume. The idea here, when we perform these trends, of course, this is a regular practice in the industry to do rock typing using poro-perm trends. But the idea, when we increase all the digital computations in the different volumes, if we apply the right quality controls, we will be able to get a much broader amount of data to support these trends specifications here. And then I cannot avoid talking about how we can QC, and of course I won't be able to disclose our QC steps here, but what I can say about this is that one major point for us is to be sure that we can capture the major features of the porous through size distribution, and with that we use the mercury injection capillary pressure as a standard point in order to compare our digital calculations in the pore through system for the digital volume and what we get for the different parts of the sample. And before moving forward to the what we call the digital scale and how digital technologies will support multi-phase flow simulations, I thought it would be useful to give a very brief overview of what we call scale and just two major techniques we use in scale that are the ones that we will discuss digitally later, because the audience here is very broad and I don't know if everyone is really familiar with scale. So I thought it didn't make any sense to talk about digital scale if people don't really know what's the conventional way to do this in the special petrophysics lab. So in the lab, basically, after we selected the plugs that are going through the program, we have different measurements for that will be used to support to characterize how flow will be in the different rock types and how to integrate that with the dynamic models. But I will talk about how we measure capillary pressure, two ways of measuring capillary pressure and one way of measuring relative permeability, just for reference. And usually the porous plate is one very common technique in which actually in the last webinar that I gave here in this space, we discussed a little bit more about the theories of PC and KR. I'm not gonna go through any of that here, but I will explain that what we usually do, we have a chamber with a semi-permeable membrane, and then you will have the passage of one of the fluids. And actually, if we have this sample, depending and if we are measuring force injection of the wetting or non-wetting phase, of if this will be full of water or if will be full of a non-wetting fluid, we will actually increase in different pressure steps, and then we will measure how much fluid is displaced from the core at the different pressure steps. The thing about this is that we usually need, depending on the pore through size distribution, we will need different times, of course, to achieve equilibrium, capillary pressure equilibrium, and this can be very time consuming. In complex systems, you can take many weeks to establish each one of the steps, so it can be a very long test depending on how your test is performed and how complex your rock is and the fluids that you are using. Another way that is faster to achieve is to use the centrifugal force to create this pressure difference. In this case, you can perform both imbibition and drainage too, and with that will depend which is the sample that is saturating the plug, and which is the fluid that is saturating the plug, and which is the fluid that is used as an outer phase. And then using the centrifugal force, we can get the pressure gradient required to introduce one of the fluid out from outside inside the core. And with that, we will be able to, with different correlations, relate the centrifugal force to a pressure difference, and that will be used to calculate the capillary pressure. And then if we know how much fluid is expelled from each of the rotational speeds, we will be able to calculate the saturation inside the plug. Of course, this is not as straightforward because we can see that there is this depends on the distance to the center. And of course, we will have, as the fluids enter, we will have a saturation profile here. So we have a capillary pressure and saturation profile here. So we need ways in order to back calculate what the average values are from the measurements we have. And then going to relative permeability, core flooding is the most common technique. And actually, we will confine in a core holder a plug or core sample, and actually applying a confinement pressure, what we call usually overburden pressure. And with these accumulators, we will have the different fluids that we need to inject, and with control systems to control flow rates and pressures, we will be able to flow the samples, the fluids in the samples, and then to see, to perform flow rate measurements and pressure drop measurements, and to calculate in terms of by material balance, to calculate the saturations inside the plug and their effective permeabilities for each of the phases. There are different methods to do this, and after that we need to treat the data. I'm not going to go into details about this, but just to talk about the most commonly used is a steady state. Basically, for the steady state, we will first clean the core and restore its wettability with aging, and after that, we will start performing drainage. So we will start with the core at initial saturation conditions, and with that, whenever we have the core at what we think is the right wettability conditions, and at connect water saturation, we measure the first point, that is the effective permeability to oil at the SWI. And then after that, we will change the fractional flows from 100% oil injection up to getting 100% water injection. So at this step of this, we will be able to measure when we equilibrate this and we get a constant delta P and a constant inlet and outlet flow rates. We will be able to measure saturation with material balance and calculate effective permeabilities for each of the phases, and with that, build a curve. The thing is that we need to establish first cleaning the core, that it can be a very big challenge. And then also each of the points we need to equilibrate and reach the steady state. So these tests take months to finish. So you usually don't consider any core flooding test that would be taking less than a month, particularly if you are working with cold wet cores that will take a very long time to clean. So with that introduction, we can go to see how we can support this using the digital technology. So basically, for digital scale, we use multi-phase flows simulations. In our case, we use in-house solvers that are based on the lattice-Boltzmann technique. In this presentation, we won't be giving any details about specific parameters or specific approaches from the solver. But the important thing to know is that with these simulations, by using the right volumes and using the right conditions, we can get very fast ways to simulate how the fluids will displace and locate across the pores. And we can actually visualize that throughout the simulations. Once we perform the simulations, we can calculate capillary pressure curves depending on the type of test you do, or relative permeabilities. And we can actually use in electrical conductivity solvers, we can use we can calculate electrical parameters that depend on saturation, like for example, the saturation exponent. This technique is very useful because the time reductions are dramatic. We can get up to 6 time reductions in order to build capillary pressure and relative permeability curves. And also it's very important to mention that this is customized solutions for each type of reservoir. As Carol was saying, the type of features that we observe in different geological systems are completely different, and the challenges that we find on each of them are also unique. So we need to build a customized solution or approach in order to be able to perform simulations on the pore scale and apply the right ways to integrate this all this information to get a meaningful results. Another very big advantage of digital rock analysis and the digital techniques is that we can perform simulate different scenarios and perform a broad range of simulations using the same volume. As this is, once we get the digital volume, this is a non-destructive test. So that's opposed to what we find in the core flooding experiments, that once we establish the all fluid interactions and then we flow with different fluids, we don't have any way to assure that the rock surface was not altered after that. So we need to, in order to perform different experiments in the same volume, what we need to have is twin plugs and know that they are exactly the same. Or be very sure that all the process that you are performing is completely non-reactive and doesn't have any strong rock fluid interaction. Here, once we have the digital volume, we can change the parameters and perform several simulations. So that's a very useful tool because, for example, we can change fluid properties such as interfacial tension or fluid viscosity and to see how this affects the displacement. And also, we can modify wettability, rock fluid interactions, and this will affect how the fluids snap off and the amount of trapped fluids in the porous system. That's what we call sensitivity analysis, and as you can see here, we can change the wettability, for example, and create a family of curves, and we can observe the impact of this in the crossover point or in the endpoints and on the overall relative permeability curves. Also, we can represent complex cases. So as we know, there are some type of rocks that are very challenging for the lab. Like, for example, in the cases of fracture systems that you don't know exactly what's the contribution of the fractures towards the whole porous flow system that you want to represent. And also very heterogeneous and bubular spaces in which you don't have any way to flow evenly across the whole porous system, and other types that won't be able to withstand the confining pressure or that get damaged after you take them out and if you don't use the right conditioning. So in these cases, the digital technology can support characterizations by performing simulation in this type of volumes. Also, we can get complex scenarios, like for example, the ones in which mineralogy and course of flow size distribution affect the wettability and how the fluids will flow. So in that case, we can model wettability dependence on the porous system or on the phases that we identify in the rock. And phases by phases, I talk about mineral or mineral porous phases. And also, we don't need to forget that this is not a technique that aims to replace the conventional SCAL or the petrophysical analysis that we do in the lab. This is an idea to work together to improve the representability, and by getting faster results and by identifying which are the key controls for the flow, we can optimize the lab routines, we can improve the quality control of the results that we are getting, and we can know where to trust more and actually select which experiments we are going to perform and on which samples with a more reliability. So that will reduce the overall uncertainty of the characterization of the reservoir. And just to finish, I will present a very brief case study. This is a very summarized case study, but the idea here is to show an integrated program between physical and digital. And in this case, it was a well that was going through, it has 4 whole core segments that were representing 3 layers with different permeabilities. And the idea here was to characterize all of them and then to perform an integration. So first, the dual energy CT scan was performed, and together with other petrophysical data, it was used to identify the flow units. And after that, the plug selection was carried out, and a multi-resolution micro CT scan was performed, going from the plug scale and reaching up to 500 nanometer scale. Then the simulations of flow were performed at the pore scale, and then upscaling was carried out in order to reach the whole segment of the core. For the capillary pressure, simulations were done for primary drainage, and then for rel perms they were done for imbibition. And here we can see for the 3 layers, the top, the intermediate, and the bottom layer, we can see the results of capillary pressure. We can see in orange the digital rock analysis curves obtained for the volumes, and then we can see the centrifuge curves obtained in the lab for the different plugs. So we can see a very good agreement in the results. We can see a good agreement both in the displacement pressure, but also in the endpoints, asymptote here close to the connect water saturation, giving us a very good agreement between both the physical and the digital results. And then for the relative permeabilities, the wettability was identified as a mixed wet by the laboratory. So that was the condition that was used to perform the simulations. So at the pore scale, we did the imbibition, and then there was an integration and upscaling that I will show in a few seconds. So we can see here again the top, the intermediate, and the bottom layers. The intermediate layer was more complex in terms of pore perm. So we can see that from the top and the bottom layer, there's a very good agreement in the endpoints and the crossover, both from the lab and from the digital simulations. And for the intermediate layer, that was a tight and more heterogeneous one. The laboratory retrieved an all-wet behavior, and that it was agreed that it was due limitations in the lab in order to get an effective cleaning and restoring of the initial wettability in order to get the representative results. So in this case, we think that the digital rock analysis is more consistent, keeping the wettability behavior than the laboratory. And then in the end, we can see here, this is two scenarios of wettability modeling a composite of the whole system, of the whole blocks. This was performed through upscaling. And of course, we don't have any values to compare this in the lab, because this type of systems are not water flooded in the lab. There is no size of core holder for this. But this is another way we can use the digital rock technology in order to get a representation of a greater scale. So as the points for this, we have a good agreement, and it will increase the QC of our conventional petrophysics skull. And then also it's very important to talk about time optimization, because the digital workflow had results in 6 months and the physical in 6 years total. So it's very good to know to see how this having this information in a shorter time can help us for decision making. And then what we can do in terms of production enhancement, well, we can simulate at the pore scale, considering very complex phenomena, so wettability changes, and also IFT and IFT reduction up to near miscibility conditions. So we can simulate near miscible flow, and then also we can obtain the relative permeability curves in a very short timeline, so that can help to generate scenarios and to know what are the next steps, or to obtain preliminary models faster. and also upscaling the rel perms to plug and then to a larger scales in order to input this in dynamic models. So as a conclusions, just to take home messages, the array is a very valuable tool. We can optimize time and resources, and it can aid in reservoir development. So we can support both the geological and static models and the dynamic models by enhancing the characterization of the reservoir. As in complex cases, we will be able to capture features that in some simpler cases may not be important, but in some others may be decisive to get better or lower uncertainties. So multi-resolution scans and a rigorous QC of the volumes are really, really important in order to get results that you trust. And that is something that we need to really, really address whenever we apply this type of technologies. And then the integrated solutions, they can be customized for different challenges. So this presentation was completely general. We know that the audience here is general, so we didn't want to address any type of particular assets, but we can work in this technology. We work with shales, we work with carbonates, heterogeneous carbonate, we work with turbidites, with a lot of type of we work with poorly cemented sandstones. So we have a lot of challenge that we can address with this type of technology. So in all this digital transformation that is the way ahead in the oil and gas industry, we believe that the array is one of the key game players to achieve this digital transformation. And with that, we will be happy to discuss any comments or questions.
Thank you, Caroline. Thank you, Santiago, for the presentation. We have already some questions here on the chat. I will start with the first one from Felipe Cruz. Can you talk a little more about the quality control to check the different regions that are being characterized? Is there a petrophysical criterion or ground truth by which these regions are compared to?
Yes, let me just stop sharing. How do I stop sharing my screen here?
I believe it's in the bottom, maybe, or in the upper part of your screen. There will be a button that says stop sharing.
So are you still seeing my screen?
Yes.
Okay, well, doesn't matter. It's fine. I wanted to see the people, but it's okay. You can see my camera, right?
Yes.
Okay. So the question was about the QC, right?
Okay. There you go.
Yeah, someone did it for me. Thanks.
Yes.
Okay, so regarding the QC of I think it was referring to the digital volumes, right? So basically what we usually need to assure is that some key properties of flow, and that it will depend on what type of REV you want to get, right? If you are upscaling electric properties, maybe the QC won't be the same that if you are upscaling flow properties or elastic properties or any other type. For the flow properties that are the most important for this presentation, usually what we do is we will select a certain amount of volumes, and then we will select a certain amount of sub-volumes there with different sizes, and we will perform some key parameters of flow that we will use to QC. For example, Swanson permeability or some other key points that we assume that can be used to characterize in terms of flow. What we use is a statistical analysis then in order to the size of and location of the different volumes, and we get trends, and we see the variance of these fast simulations across the volumes. And when we get a huge number of volumes, we can see whenever for each volume it has the lowest variance across the sub-volumes that it has. So whenever we get a volume that has a very, very small variance of the key points across the sub-volumes within, we will assume that that's a good volume for simulation, because it's keeping the main flow properties across the entire volume distribution. I don't know if that was clear enough. It's kind of hard to explain like this, but it's kind of a statistical analysis to see if the properties are kept across the whole distribution of the volume.
Yeah, and we use also the same integration of some physical parameters to support us to QC, right, Santiago? So, for example, if I think the second question, it looks like the first question, but I think it's more inside of the limitations of voxels and images that I can see here. And actually, what we do, for example, we can clearly see a link between the textural volume of the images with the rock properties, right? And the clear link from that, it's seen, for example, when we see a highly complex image with different structure distributed around it, and we can clearly see an isotropy in the image. When we run an N-trim to MICP, a mercury injection capillary pressure for this rock, we will see a curve with 3 or 4 peaks for different pore size distributions. So we can clearly see when the samples are presenting textural distributions with anisotropy, we can clearly see MICP curves with multiple pore systems. So what we do to make sure that we capture all of this is to make subvolumes that is capturing all the peaks of 3 or 4 cumulative curves that we can see in the MICP. And we use that also to calibrate the volume that we are using. So we run digitally and we actually compare with the MICP. You can see that in Santiago's ARCAL slide, a comparison of a digital and a physical MICP curves. And so we have this parameter also to actually support us in the QC to make sure that we are capturing all the multi-scale pore volume of, if you have only, for example, a curve with only one type of pore, a modal pore system, then we do know that it's reliable to use only one volume because we only have one pore system that is dominating your rock volume in your image. So this is how we connect through scales and combine also with physical results. I don't know if it's clear enough, but yeah, just to complement what Santiago was saying.
Thank you, Caroline. Yeah, Felipe saying it was clear. Thank you, Professor. Thank you, Caroline. Okay. Then we have a question from Ritesh Bhakta. Thank you for the informative talk. I have a question in regards to scaling, which I believe is one of the greatest challenges with DRA. Unlike physical testing, image analysis is bound by maximum voxel size and minimum image size, limit to detectability or seeability. During your downscaling process, your invariable will miss pores that fall in between your image resolutions. This will result in incorrect porosity fractions when upscaled, which is a simple scalar property, and even a larger margin of error for vector values computed during digital scales such as capillary pressure and relative permeability. How do you interpolate or overcome this challenge?
Okay, I can give first an idea, then maybe Carol, if she wants to complement about the other parts. But yes, this is a key, it's a very, very important point. And actually, we do apply different methods, but for, as you said, for the static properties, it's not so hard to be able to overcome this, because actually you have ways to link across the scales, right? As Carol showed in the beginning, we don't only apply one resolution scale or pore scale resolution scans. We have core scale resolution scans, and we have dual energy, and that allows us to have bounding points at different scales that we can relate with properties. Like, for example, we have ways to relate, of course, the CT response of materials to materials density and porosity, if we know somehow the mineralogy or mineralogy distribution that we expect, right? So in this type of way, it's a mathematical problem. And I'm not saying it's easy, but you have ways to do that, right? Once you have bounding points, and the important thing is that you are sure that you are capturing the whole resolution that you need, and then you need to be consistent in the ways that you upscale this mathematically. And there are some ways to do that. And as I said before, we use some other support information, such as how we relate the CT scales to physical properties. And of course, you need to know information about the type of geological structures you are upscaling, right? Because it's not the same whenever you have a valvular fluxions or whenever you have an isotropy and a kVkH ratio that is completely heterogeneous across the well. It's not the same that whenever you are, but whenever you are upscaling a very, very well-behaved pore system that behaves the same across the whole well. And with that, once you have the right bounding points and you have the information about what type, how to relate the porosity and then permeability to other scales, it's a mathematical problem. And we actually have we developed this. Actually, it's not a straightforward answer that applies for everything. We developed this as we have development teams at Halliburton working on this as part of our work in how to integrate scales. Then when you go to, as you said, when you go to more complex properties such as multi-phase flow properties for dynamic models, that is a whole different story, and that is much more complex. In that case, we need to have a very good QC of the pore scale simulations in order to avoid having garbage that will populate our models. But then, depending on how complex the problem is, we will have different methodologies. If we are simulating in quite, for example, in a laminated system that have very well-behaved porous structures, we can actually use, depending on how we are taking this information, and we can actually use analytical models in order to go to a larger scale. But you need to be really careful on how you do that. So yeah, basically, it's a very hard, very complicated thing, and there's not only one answer. But the thing is that you have ways to do this, but it's a customized solution. That's what I wanted to say. So it's a very specific and it depends very much on the type of features you have, and then of course, to calibrate the model, something that I didn't say. The idea of this whole characterization is to go faster and to improve reliability, but we still use physical measurements to calibrate some points of our workflow. So it's not completely independent of physical measurements. So we have some ways in between. For example, we use plugs to calibrate both ways, how do we integrate the pore to the plug, and then how we integrate the plug to the log, for example. So in that case, whenever we go through scales and we try not to increase the uncertainty so much, we are not going blind. We have the plug as a way between, and then also we have wireline logs and we have other support information. We don't only increase the scales without any type of information or fixing points information. But yeah, it's a very complex phenomena, and sometimes we also get support by reservoir simulators to travel across the scales, right? We have internal points of calibration. Whenever we do simulations in the plug, we use a reservoir simulation, and then we know how to take this to a larger scale. So yeah, those were my thoughts about that. I don't know if Carol or anyone else wants to say anything.
No, I just want to actually just to corroborate what you say, Santiago. It's the key question is before what you want to characterize, what you're looking for to characterize, and then not only characterize with image, but with image as supported, right? With image and computation as support. So for example, if you're going to analyze a tight rock formation, there will be a different workflow than from pre-salt formation, for example, that is full of bugs. And so the types of features that you're going to segment and test and test with physical measurements to calibrate will be a totally different workflow, right? So for example, we can use NMR also from plugs and to link with cores and to actually see digital curves from ICP are corroborated with both, right? So this will be, for example, one interpolated point of it. And if we're doing this for type rock formations, we would use SAM pictures and XRD to populate it as well, and to investigate into nano resolution in this case. So the digital technology here, it's just a tool to optimize and fasten and leverage results, but it's not here to substitute physical measurements. It's just here to facilitate process and to integrate with what we have in hands to acquire even more informations that are in the rocks that we can extract from this high resolution image and computations.
Okay. Thank you, Caroline. Thank you, Santiago. We do not have more questions on the chat, but if the audience wants to make another question, please feel free, unmute yourself. Okay, I believe there is no more questions. I do have a question regarding the dynamic parameters, especially as Santiago said, it's quite complex, right? And as we are talking about the pore scale, there's a lot of tortuosity, complexity, and the mathematical models, they struggle. It needs to be a very robust model. Lattice-Boltzmann or Navier-Stokes are great, but do you make any simplification before running your simulators, or you use the entire geometry?
Simplifications in terms of what? Of rock geometry?
Yeah, in the geometry. For instance, ball and sticks or something like that.
Oh, no, yeah, we have many ways to do that, but actually what we use, we can actually get to the almost correct geometry and applying the right boundary conditions. But what is key for that is how to model what happens when each particle of each fluid will bound to the boundary conditions, right? What happens when it touches the rock? So that's what we changed, because modeling this for single phase is not the challenge, right? Actually, it doesn't have anything very very difficult in terms of mathematical model. But the thing is how to model capillary pressure, capillary effects there. And the complex thing, and where there are some approximations, is how you will simulate what happens at the boundaries what will happen in the contact between the fluids and the rock. And yeah, we use some parameters, and we have some ways of applying wettability distributions, as I was saying during the presentations. But yeah, there are some approximations about this. For example, one of the input parameters is contact angle distribution for each mineralogical phase. And that's a huge approximation in terms of how you distribute, because we know that, well, people are really questioning what is a contact angle distribution, what is a contact angle value. Usually you should work with contact angle functions. And also to model the snap-off, we need to assume which phases will form fluids at each point of the rock. So there's another approximation there, because you need to assume that there is a continuous phase and a non-continuous phase that can be trapped. But the thing is, we know that for real systems, it doesn't work like this. You don't have a continuous film of a fluid across the whole rock system whenever you have a heterogeneous in mineralogy. So we have those type of approximations in terms of multi-phase fluid flow. And we also developing other type of mathematical solver, but that actually is not my area of expertise. We can invite one of our developers to this seminar if you want. We have many very talented mathematicians that work with us.
Okay, that's great, Santiago. That's great. Thank you. And I have a last question here about, are you guys exploring also the use of machine learning techniques or artificial intelligence in your workflow?
Yes, we are. We actually already have two different fronts from it. and also in different scales. We have the machine learning apply to cluster the high resolution core logs, for example, that we call faces ML. So, and we cluster not only the images logs, but also the ROBI and PE logs, and along with physical measurements logs directly from the core, for example, gamma ray, right? So, and we call faces ML. And as more information that we do have, the faces respond is more accurate, right? So we also integrate digital with physical measurements in this parameter. And we have a second one that we call fabrics ML, that it's more regarding the complexity of the pore systems. So it's a machine learning that understands the differentiation of distribution of fabrics that are going on inside of a plug, for example. So if you have a multimodal pore system, the machine learning can use the images to actually divide it in different patches, and afterwards just to clusterize as different groups and to show how many fabrics that we have, that supposedly will give you how many pore time systems you have. And afterwards, it can see not only in the image, but how it's distributed on your volume, right? So once we capture that fabrics and compute all the properties, we can put back inside of the machine learned model, so we can upscale into the plugs distributed in the plug volume. So both texture ML and fabrics ML are examples of how machine learning and knowledge model are being integrated with the technology. We're not presented here, but yes, we are two fronts that we are also developing inside this technology. Santiago, please feel free to add your comments if you want to.
No, it's exactly that. And those are the two really mature technologies that are actually commercial at this point. And people can really present, and we have a project implementation of this. And also there is, as I was saying, we have a development team, so there always appear new applications for machine learning or deep learning, like for example, even at the pore scale, pore shape recognition, this type of things, or imaging recognition, any type of
fingerprints.
Yes. So we have now some developments, but for sure in the future there will be many more applications.
Okay. Well, Santiago, Caroline, once again, thank you so much. Now we will ask the audience to turn on the cameras, as we would like to take a beautiful picture. And Rita, please let us know when you're going to take the picture.
Okay, just give me some minutes. I will take one now. Let me take another one. Just the third one, please. Okay, that's it. Thank you.
Thank you, Rita. And thank you all. Just to let you know that our next webinar will be about carbon capture, utilization, and storage. It will be under the umbrella of the Beyond the Borders initiative. It's an initiative actually funded by the young professionals of SPE Europe, and it will be on the end of May. So we hope to see you all there, and please stay tuned for our upcoming events. Please follow us in our social media. And thank you so much. Enjoy your weekend. Caroline, Santiago, thank you.
Thank you, Claudio.
Thank you.
Thank you very
Bye-bye.
much.
Everybody.